In this video, we're going to look at a concrete example of diagonalizing a matrix. Now, let's just kind of remind ourselves what that means. So first of all, let's step back to the concept of a similar matrix. So we would say A is similar to B if and only if B can be written like this. So B can be essentially factored into this special product, right? B equals P inverse times A times P. Now, if A can be diagonalized, or if A is a diagonalizable matrix, then A will be similar to a diagonal matrix. That means that there is some diagonal matrix out there that can be written in this form, right? And then similarly, just through some matrix algebra, if we wanted to go ahead and solve this equation for A, we would do pre-multiplication by P and then post-multiplication by P inverse, and we would get that A can be written as P times D times P inverse. All right, so it's really these two equations that we're going to be focused on in this video. And more so, we're going to be focused on how do we find the P and the D matrices that make this matrix equation true, right? And it turns out that the P and the D are found by those eigenpairs that we talked about recently, right? So that's what we're going to take a look at now, is what is the process for finding, or better yet, constructing the P and D matrices in this equation, and then let's actually go through an example. So here is just a brief outline of the process, right? So the first thing that we're going to do is we're going to start with our matrix A, and we're going to find the eigenvalues of A, right? So we're going to find the eigenvalues of A. And how do we do that? Remember, we get our characteristic polynomial, which is the determinant of A minus lambda I, and we're going to set that equal to 0 and find all the values of lambda that satisfy that. And then 2, we are going to find the corresponding eigenvectors, right? So we're going to find the eigenvectors of A, and how do we do that? Well, for each lambda that we found in the first step, we're going to solve this corresponding homogeneous system. So A minus lambda I is going to be our coefficient matrix. The V are the vectors that we're going to be finding, and it's always going to be a homogeneous system. And then, once we have the eigenpairs, then this is how we construct P and D. So P is going to be the matrix where the columns are going to be the eigenvectors of our matrix, right? So if we start with an n by n matrix A, then P is also going to have to be n by n, and here are its n columns. It's going to be V1, V2, dot, 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 Vn, right? So the eigenvectors will become the columns of our special matrix P. And then the diagonal matrix, step 4, D is going to be the diagonal matrix. And what are the entries on the main diagonal? Well, not surprisingly, they're going to be the eigenvalues. So like in the first row, first column, we're going to have lambda 1. In the second row, second column, we're going to have lambda 2. And then in the third row, third column, we'll have lambda n, right? So you can see just in this process here, we're going to need, n eigenvectors to form this n by n matrix P, and then the corresponding eigenvalues will be there, right? Now in this video, we're not going to really talk about the theoretical foundation for this process, but you can see that what if we can't find n eigenvectors? What does that mean about the original matrix A, right? But that will be addressed in a subsequent video. For now, let's just focus on this process. So for the example, here's what we're going to use. We're going to use the matrix, let's just do a 2 by 2 matrix, 1, 5, -2, 8, right? And we're going to walk through these 4 steps. Now, for a 2 by 2 matrix, we have the nice formula that the characteristic polynomial is simply lambda squared minus the trace of the lambda, and I'm sorry, the trace of the matrix. The trace of the matrix is 1 plus 8, and then that's times lambda, and then plus the determinant of the matrix, which is 1 times 8 minus 5 times negative 2. And then this simplifies to lambda squared minus 9 lambda plus 18. And there we go. So now let's say if we set our polynomial equal to 0, what do we end up getting? And it looks like we can factor that. So that's going to be lambda squared minus, not lambda squared, just lambda minus 6, and then the quantity lambda minus 3, that's equal to 0. So we have our 2 real distinct eigenvalues. So lambda is either 6 or lambda is equal to 3. So step 1, done. Step 2, now we have to find the eigenvectors that correspond to each of these. So now we're going to set up our homogeneous system. So let's do lambda equals 6 first. So as you know, just looking at this coefficient matrix, we're simply subtracting lambda from the entries on the main diagonal. So it's going to be 1 minus 6, so that's negative 5, and then we'll have a 5 there. It's going to be a homogeneous system. So we have a 0, and then negative 2, and then 2, 0. And then it's not hard to see that if you put this in RREF, what will happen is you'll have 1, negative 1, 0, and then 0, 0, 0. So we can say that our x2 can be our free variable, and then x1, in this case, is also going to be t. So here is our v1, right? It's any vector of this form, any non-zero vector of this form. If we take out the t, then we can use the vector 1, 1 as a basis for all the eigen vectors that correspond to lambda equals 6. So I'm just going to use the 1, 1 as our basis vector. So here's our first eigenpair, right? So it's like we know one column of P, and we know the one entry on the main diagonal in our D matrix, right? Well, we repeat that process. Let's do this now when lambda is equal to 3. So now we're going to subtract 3 from the entries on the main diagonal. That gives us negative 2, 5, negative 2, 5. Again, if you just love working with RREF, and who doesn't love working with RREF, we end up having 1, negative 5 halves, 0, and then 0, 0, 0. Right? So again, we can use our second variable as our free variable, and then in this case, x1 is going to be 5 halves t. So let's see if we can extract a basis for the second eigenvector. So we'll have 5 halves t, we'll have a t there, factor out the t, and we have 5 halves and 1. Now, if we don't want to have fractional entries in our eigenvector, which then means we would have fractional entries in our p, remember we could take any scalar multiple of this. So I'm going to just double this, and I'm going to say, okay, the eigenvector, the basis for the eigenvectors that correspond to lambda equals 3 is 5, 2. Right? That way at least we'll start out with a p that has nice integer entries. So now let's define our P matrix. So we're going to let P be equal to this 2 by 2 matrix. So I'm going to take 1, 1 as the first column, and then 5, 2 as the second column. And then the diagonal matrix, now I have to make sure that in the 1, 1 position of the diagonal matrix, I use the eigenvalue that corresponds to the first column in our P matrix, and that will be 6. And then similarly, entry that's in the second row, second column, that's going to be our 3. And we know for a diagonal matrix, the other two entries would have to be equal to 0. So that's the P and the D, right? But what I also want to do is to verify that this whole thing works, right? Now, let me go back up. I just realized I misspelled, I don't know why I put a G there. That should be a D. There we go. So here's what we're going to do to verify this. We're going to use this equation because we've essentially found P and D. We still need to find P inverse. We'll do that next. And then we're going to do our matrix product here and see that it actually works, that it gives us back our original matrix, right? So that's the verification. But as far as finding the P and the D, we're done that part of the process. So now let's look at P inverse. Now, because P is a 2 by 2 matrix, remember we have a nice formula for the inverse of a 2 by 2 matrix. So it's 1 over the determinant, which of this matrix, which is 2 minus 5. So it's 1 over 2 minus 5 times the adjoint of this matrix. Now, the adjoint of a 2 by 2, you have to do a little switcheroo there. You interchange your entries on the main diagonal, and then you change the sign. You negate the entries on the off diagonal. So here is P inverse. And in fact, I think what I'm going to do is let's not distribute the negative 1/3. Let's just keep it as negative 1/3, and then times 2, negative 5, negative 1, 1. And the reason I'm going to do this is just that it will make the arithmetic a little bit easier in our process, right? So here's what the theory tells us. It tells us that our original matrix, so therefore our original matrix 1, 5, negative 2, 8 can be written as this special product. The original matrix now is going to be P, so it's going to be 1, 5, 1, 2 times the diagonal matrix, which is 6, 0, 0, 3, and then times the negative 1/3 times the 2, negative 5, negative 1, 1. Now, we have some algebraic properties that allow us to, kind of handle this negative 1/3 more efficiently. And one thing that we can do is take this scalar multiple and put it in front of our product here. So I'm going to do that. And I'm going to do that last, but then the other two products, which are matrix products, we have the associative property that allows us to group them however we like. So here's what I'm going to do. I'm going to choose to do the 1, 5, 1, 2 times 6, 0, 0, 3. I'm going to do that product first, and then seeing what that looks like, decide whether I'm going to distribute the negative 1/3 or if I'm going to do this matrix product after, right? So the nice thing is you can sort of look at the numbers and ask yourself from a computational standpoint, what is most efficient, right? So that's why we like these algebraic properties. They give us some flexibility. So let's do the first matrix product that I have there in parentheses. So I'll have 6 plus 0, so I have 6 plus 0, and then 0 plus 15, so I have that, and then again another 6 plus 0, so 6 plus 0, and then a 0 plus 6, so 0 plus 6, all right? Remember, it's actually pretty easy to multiply entries by a diagonal matrix, right? Because you have all those zeros. All right, so we have 2, negative 5, negative 1, 1. All right, so then let's go through and so if we simplify the entries here, we'll have 6, 15, 6, and 6. And then looking at these 4 entries, they're all multiples of 3. So it might actually be a nice thing to just go ahead and distribute the negative 1/3 right now. So that will give us negative 2, negative 5, negative 2, negative 2. And then let's go ahead and multiply by 2, -5, -1, 1. All right, so last matrix product, what do we have? We have -4 plus 5, and then we have a 10 minus 10, and then we have a -4 plus 2, and then we have a 10 minus 2. And when we simplify our entries, we end up having 1, 5, -2, and 8. And there you go, and we are happy. Score 1 for eigenpairs, right? So our factorization, right, actually works. All right, so we verified that A is equal to P times D times P inverse, which also implies that D, our diagonal matrix, is equal to P inverse times A times P. So if we wanted to, right, we could have used this equation to verify that the diagonal matrix that we came up with can be written in this form, right? And that's our process, right? So the only thing that can make this process a little bit more tedious is if you have larger matrices, and therefore the algebra becomes a little bit more tedious. So in subsequent videos, we're going to take a look at kind of some of the theory, not too heavy on the theory, but why does this work, and when will it work, right? Or what are some of the pitfalls? So if you want to see a little bit more about this diagonalization and why it works, hop over to the next video, and I'll see you then.